Is there a link between human mind and quantum physics? Well, it sounds kind of weird. First of all, what is quantum physics? Well, quantum physics is that really weird discovery that observation of a wave actually collapses it down into a particle. We're talking about the smallest little units, those little things that we call particles, but when you get in close and you observe them, well, when you're not observing them, they look like waves. When you do observe them, they look like particles. And so here's this crazy idea that caused Einstein to wonder if God plays with dice, and if what's happening at the very smallest levels could be very different than what we experience on the larger level. At the large level, we operate basically on Newtonian physics, that we can plot the course of the solar system using Newtonian physics, etc. But when we get down to those smallest, tiniest particles, things behave in a very different way. And so there's some new research that there is a strange link between the human mind and quantum physics. Now, as somebody who is interested in the Bible, that's me, I find this very exciting because I come across these weird passages like Jesus saying, according to your faith, let it be done to you, and things like, if you believe, then you'll receive, or things like, pray for whatever, and if you believe, you'll receive it. Really weird statements that seem to defy all human logic, and yet we see Jesus saying that let it be according to your faith, even places where he tried to heal people, and because they didn't have faith, he wasn't able to heal people. What's going on there? Well, let's take a look at this article. This is according to BBC.com, and this is on their Earth section. The strange link between human mind and quantum physics. Nobody understands what consciousness is or how it works. Nobody understands quantum mechanics either. Could that be more than coincidence? Well, let's see here. I cannot define the real problem, therefore I suspect there's no real problem. But I'm not sure there's no real problem. The American physicist Richard Feynman said this about the notorious puzzles and paradoxes of quantum mechanics, the theory physicists use to describe the tiniest objects in the universe. But he might as well have been talking about the equally knotty problem of consciousness. Some scientists think we already understand what consciousness is, or that it is a mere illusion. But many others feel we have not grasped where consciousness comes from at all. Some scientists think, that the perennial puzzle of consciousness has even led some researchers to invoke quantum physics to explain it. That notion has always been met with skepticism, which is not surprising. It does not sound wise to explain one mystery with another, but such ideas are not obviously absurd, and neither are they arbitrary. For one thing, the mind seemed, to the great discomfort of physicists, to force its way into early quantum theory. What's more, quantum computers are predicted to be capable of accomplishing things ordinary computers cannot, which reminds us of how our brains can achieve things that are still beyond artificial intelligence. Quantum consciousness is widely derided as mystical too, but it just will not go away. Quantum mechanics is the best theory we have for describing the world at the nuts and bolts level of atoms and of subatomic particles. Perhaps the most renowned of its mysteries is the fact that the outcome of a quantum experiment can change depending on whether or not we choose to measure some property of the particles involved. When this observer effect was first noticed by the early pioneers of quantum theory, they were deeply troubled. It seemed to undermine the basic assumption behind all science that there is an objective world out there, irrespective of us. If the way the world behaves depends on us, or if we look at it, what can reality really mean? Some of those researchers felt forced to conclude that objectivity was an illusion and that consciousness has to be allowed an active role in quantum theory. To others, that did not make sense. Surely Albert Einstein once complained the moon does not exist only when we look at it. Today, some physicists suspect that whether or not consciousness influences quantum mechanics, it might in fact arise because of it. They think that quantum theory might be needed to fully understand how the brain works. Might it be that just as quantum objects can apparently be in two places at once, so a quantum brain can hold on to two mutually exclusive ideas at the same time. These ideas are speculative, and it may turn out that quantum physics has no fundamental role either for or in the workings of the mind. But if nothing else, these possibilities show just how strangely quantum theory forces us to think. And this is the famous double slit experiment. When you shine a wave through a double slit, then it appears, as you can see there on the back screen, you have these interference waves. But when you start to shoot single atoms through it, or single electrons, excuse me, what happens is when they are not looking, when they're not observing it, then it appears as a wave. But when they do observe it, of course with instrumentation, then it appears as particles. That's what's so crazy about this. So the most famous intrusion of the mind into quantum mechanics comes in the double slit experiment. Imagine shining a beam of light at a screen that contained two closely spaced parallel slits. Some of the light passes through the slits, whereupon it strikes another screen. Light can be thought of as a kind of wave, and when waves emerge from two slits like this, they can interfere with each other. If their peaks coincide, they reinforce each other, whereas if a peak or a trough coincide, they cancel out. This wave interference is called diffraction, and it produces a series of alternating bright and dark stripes on the back screen, where the light waves are either reinforced or canceled out. This experiment was understood to be characteristic of wave behavior over 200 years ago, well before quantum theory existed. The double slit experiment can also be performed with quantum particles like electrons, tiny charged particles that are components of atoms. In a counterintuitive twist, these particles can behave like waves. That means they can undergo diffraction when a stream of them passes through the two slits, producing an interference pattern. Now suppose that the quantum particles are sent through the slits one by one, and their arrival at the screen is likewise seen one by one. Now there is apparently nothing for each particle to interfere with along its route. Yet nevertheless, the pattern of particle impacts that build up over time reveals interference bands. The implication seems to be that each particle passes simultaneously through both slits and interferes with itself. This combination of both paths at once is known as a superposition state. But here is the really odd thing. Here it is. So let me go back there. Sorry about that. If we place a detector inside or just behind one slit, we can find out whether any given particle goes through it or not. In that case, however, the interference vanishes simply by observing a particle's path. Even if that observation should not disturb the particle's motion, we change the outcome. The physicist Pascual Jordan, who worked with quantum guru Niels Bohr in Copenhagen in the 1920s, put it like this: observations not only disturb what has to be measured, they produce it. We compel a quantum particle to assume a definite position. In other words, Jordan said, we ourselves produce the results of measurements. If that is so, objective reality seems to go out the window. And it gets even stranger. If nature seems to be changing its behavior depending on whether we look or not, we could try to trick it into showing its hand. To do so, we could measure which path that a particle took through the double slits, but only after it has passed through them. By then, it ought to have decided whether to take one or the other path. An experiment for doing this was proposed in the 1970s by the American physicist John Wheeler, and this delayed choice experiment was performed in the following decade. It uses clever techniques to make measurements on the paths of quantum particles, generally particles of light, called photons, after they should have chosen whether to take one path or a superposition of two. It turns out that just as Bohr confidently predicted, it makes no difference whether we delay the measurement or not. As long as we measure the photon's path before its arrival at a detector is finally registered, we lose no interference. It is as if nature knows not just if we are looking, but if we are planning to look. Whenever in these experiments we discover the path of a quantum particle, its cloud of possible routes collapses into a single well-defined state. What's more, the delayed choice experiment implies that the sheer act of noticing, rather than any physical disturbance caused by measuring, can cause the collapse. But does this mean that true collapse has only happened when the result of a measurement impinges on our consciousness? The possibility was admitted in the 1930s by the Hungarian physicist Eugene Wigner. It follows that the quantum description of objects is influenced by impressions entering my consciousness, he wrote. Solipsism may be logically consistent with present quantum mechanics. Wheeler even entertained the thought that the presence of living beings, which are capable of noticing, has transformed what was previously a multitude of possible quantum paths into one concrete history. In this sense, Wheeler said we become participants in the evolution of the universe since its very beginning. In his words, we live in a participatory universe. To this day, physicists do not agree on the best way to interpret these quantum experiments, and to some extent, what you make of them is, at the moment, up to you. But one way or another, it's hard to avoid the implication that consciousness and quantum mechanics are somehow linked. Now, again, what I find so intriguing is that Jesus came and he did these miracles, and when he went to Nazareth, it says that he did not do many miracles there because of their unbelief. Now, we're talking about the God of the universe, right? I believe that Jesus is the second person of the Godhead. He is the incarnation, the Emmanuel, God with us. And here he comes along. He goes to Nazareth, and people there are kind of making light of him. Isn't this the carpenter's son? And, we know who this is. And they don't have faith. And so he doesn't, or says he can't. He couldn't do many miracles there because of their unbelief. And yet in other places where people are believing, they have faith, it says that seeing that he had faith to be healed, he healed him. Or when the friends of the paralytic let the man down through the roof, what did they do? What did Jesus say? He said he saw that he had faith, and he said, son, your sins are forgiven, and then he healed him. The man had faith. In every instance, it's always about your faith has healed you. Very strange words from the creator of the universe, the God of all creation, the all-powerful one. He could just snap his fingers and make everything happen. And yet it seems that that's not how his universe works. Right? It's not that God has any limitation of power, but it seems that he has in some way created the universe that we are participants in this universe, that we are co-laborers with him in a way that we don't fully understand. These are the implications of the Bible, and yet modern science seems to be picking up on that very idea. Beginning in the 1980s, the British physicist Roger Penrose suggested that the link might work in the other direction. Whether or not consciousness can affect quantum mechanics, he said, perhaps quantum mechanics is involved in consciousness. So there's an idea. What if, Penrose asked, there are molecule structures in our brains that are able to alter their state in response to a single quantum event? Could not these structures then adopt a superposition state, just like the particles in the double slit experiment? And might those quantum superpositions then show up in the way neurons are triggered to communicate via electrical signals? Maybe, says Penrose, our ability to sustain seemingly incompatible mental states is no quirk of perception, but a real quantum effect. After all, the human brain seems able to handle cognitive processes that still far exceed the capabilities of digital computers. Perhaps we can even carry out computational tasks that are impossible on ordinary computers, which use classical digital logic. Penrose first proposed that quantum effects feature in human cognition in his book 1999 book The Emperor's New Mind. The idea is called OR, which is short for orchestrated objective reduction. The phrase objective reduction means that, as Penrose believes, the collapse of quantum interference and superposition is a real physical process like the bursting of a bubble. OR draws on Penrose's suggestion that gravity is responsible for the fact that everyday objects such as chairs and planets do not display quantum effects. Penrose believes that quantum superpositions become impossible for objects much larger than atoms because their gravitational effects would then force two incompatible versions of spacetime to coexist. Penrose developed this idea further with American physicist Stuart Hameroff. In his 1994 book, Shadows of the Mind, he suggested that the structures involved in this quantum cognition might be protein strands called microtubules. These are found in most of our cells, including the neurons in our brains. Penrose and Hameroff argue that vibrations of microtubules can adopt a quantum superposition, but there is no evidence that such a thing is remotely feasible. It has been suggested that the idea of quantum superpositions in microtubules is supported by experiments described in 2013, but in fact those studies made no mention of quantum effects. Besides, most researchers think that the OR idea was ruled out by a study published in 2000. Physicist Max Tegmark calculated that quantum superpositions of the molecules involved in neural signaling could not survive for even a fraction of the time needed for such a signal to get anywhere. Quantum effects such as superposition are easily destroyed because of a process called decoherence. This is caused by the interactions of a quantum object with the surrounding environment through which the quantumness leaks away. Decoherence is expected to be extremely rapid in warm and wet environments like living cells. Nerve signals are electrical pulses caused by the passage of electrically charged atoms across the walls of nerve cells. If one of these atoms was in a superposition and then collided with a neuron, Tegmark showed that the superposition should decay in less than 1 billionth of a second. It takes at least 10,000 trillion times as long for a neuron to discharge a signal. As a result, ideas about quantum effects in the brain are viewed with great skepticism. However, Penrose is unmoved by those arguments and stands by the OR hypothesis. And despite Tegmark's prediction of ultra-fast coherence in cells, the other researchers have found evidence for quantum effects in living beings. Some argue that quantum mechanics is harnessed by migratory birds that use magnetic navigation, and by green plants when they use sunlight to make sugars in photosynthesis. Besides, the idea that the brain might employ quantum tricks shows no sign of going away, for there is now another, quite different argument for it. In a study published in 2015, physicist Matthew Fisher of the University of California, Santa Barbara argued that the brain might contain molecules capable of sustaining more robust quantum superpositions. Specifically, he thinks that the nuclei of phosphorus atoms may have this ability. Phosphorus atoms are everywhere in living cells. They often take the form of phosphate ions, in which one phosphorus atom joins up with 4 oxygen atoms. Such ions are the basic unit of energy within cells. Much of the cell's energy is stored in molecules called ATP, which contain a string of 3 phosphate groups joined to an organic molecule. When one of the phosphates is cut free, energy is released for the cell to use. Cells have molecular machinery for assembling phosphate ions into groups and cleaving them off again. Fisher suggested a scheme in which 2 phosphate ions might be placed in a special kind of superposition called an entangled state. The phosphorus nuclei have a quantum property called spin, which makes them rather like little magnets with poles pointing in particular directions. In an entangled state, the spin of one phosphorus nucleus depends on that of the other. Plus, another way entangled states are really superposition states involving more than one quantum particle. Fisher says that the quantum mechanical behavior of these nuclear spins could plausibly resist decoherence on human timescales. He agrees with Tegmark that quantum vibrations, like those postulated by Penrose and Hameroff, will be strongly affected by their surroundings and will decohere almost immediately. But nuclear spins do not interact very strongly with their surroundings. At the same time, quantum behavior in the phosphorus nuclear spins would have to be protected from decoherence. This might happen, Fisher says, if the phosphorus atoms are incorporated into larger objects called Posner molecules. These are clusters of 6 phosphate ions combined with 9 calcium ions. There is some evidence that they can exist in living cells, though this is currently far from conclusive. In Posner molecules, Fisher argues, phosphorus spins could resist decoherence for a day or so, even in living cells. That means they could influence how the brain works. The idea is that Posner molecules could be swallowed up by neurons. Once inside, the Posner molecules could trigger the firing of a signal to another neuron by falling apart and releasing their calcium ions. Because of entanglement in Posner molecules, Two such signals might thus in turn become entangled, a kind of quantum superposition of a thought, you might say. If quantum processing with nuclear spins is in fact present in the brain, it would be an extremely common occurrence happening pretty much all the time, Fisher says. He first got this idea when he started thinking about mental illness. My entry into the biochemistry of the brain started when I decided 3 or 4 years ago to explore how on earth the lithium ion could have such a dramatic effect in treating mental conditions, Fisher says. Lithium drugs are widely used for treating bipolar disorder. They work, but nobody really knows how. I wasn't looking for a quantum explanation, Fisher says, but then he came across a paper reporting that lithium drugs had different effects on the behavior of rats depending on what form or isotope of lithium was used. On the face of it, that was extremely puzzling. In chemical terms, different isotopes behave almost identically. So if the lithium worked like a conventional drug, the isotopes should have all the same effect. But Fisher realized that the nuclei of the atoms of different lithium isotopes can have different spins. This quantum property might affect the way lithium drugs act. For example, if lithium substitutes for calcium in polar molecules, the lithium spins might feel and influence those of phosphorus atoms and so interfere with their entanglement. Let me just explain entanglement for just a moment. When two quantum particles become entangled, what happens? They've done numerous studies, numerous experiments showing that they're always going to influence the spin of the other. So these particles have what they call a spin, and when they test one, it's going to test in one direction, and the other one that's entangled with it, that's kind of joined at the hip, if you will always have the exact opposite spin. And no matter how far apart they separate these two particles, they always react immediately and always the exact opposite of the other. So they're called a quantum entanglement because they are connected. And again, no matter how far they have separated these two things, there's always been this entanglement. So it's pretty crazy stuff. So he says, if this is true, if the entanglement is true, it would help to explain why lithium can treat bipolar disorder. At this point, Fisher's proposal is no more than an intriguing idea, but there are several ways in which its plausibility can be tested, starting with the idea that phosphorus spins and polar molecules can keep their quantum coherence for long periods. That is what Fisher aims to do next. And all the same, he is wary of being associated with the earlier ideas about quantum consciousness, which he sees as highly speculative at best. Physicists are not terribly comfortable with finding themselves inside their theories. Most hope that consciousness and the brain can be kept out of quantum theory, and perhaps vice versa. After all, we do not even know what consciousness is, let alone have a theory to describe it. It does not help that there is now a new age cottage industry devoted to notions of quantum consciousness, claiming that quantum mechanics offers plausible rationales for such things as telepathy and telekinesis. As a result, physicists are often embarrassed to even mention the words quantum and consciousness in the same sentence. But setting that aside, the theory has a long history. Ever since the quantum observer and the mind first insinuated themselves into quantum theory in the early days, it has been devilishly hard to kick them out. A few researchers think we might never manage to do so. In 2016, Adrian Kent of the University of Cambridge in the UK, one of the most respected quantum philosophers, speculated that consciousness might alter the behavior of quantum systems in subtle but detectable ways. Kent is very cautious about the idea. There is no compelling reason of principle to believe that quantum theory is the right theory in which to try to formulate a theory of consciousness, or that the problems of quantum theory must have anything to do with the problem of consciousness, he admits. But he says it is hard to see how a description of consciousness based purely on pre-quantum physics can account for all the features it seems to have. One particularly puzzling question is how our conscious minds can experience unique sensations such as the color red or the smell of frying bacon. With the exception of people with visual impairments, we all know what red is like, but we have no way to communicate the sensation, and there's nothing in physics that tells us what it should be like. Sensations like this are called qualia. We perceive them as unified properties of the outside world, but in fact they are products of our consciousness And that is hard to explain. Indeed, in 1995, philosopher David Chalmers dubbed it the hard problem of consciousness. Every line of thought on the relationship of consciousness is to physics runs into deep trouble, says Kent. This has prompted him to suggest that we could make some progress on understanding the problem of the evolution of consciousness if we suppose that consciousness alters, albeit perhaps very slightly and subtly, quantum possibilities. In other words, the mind could genuinely affect the outcome of measurements. It does not in this case exactly determine what is real, but it might affect the chance that each of the possible actualities permitted by quantum mechanics is the one we do in fact observe, in a way that quantum theory itself cannot predict. Kent says that we might look for such effects experimentally. He even bravely estimates the chances of finding them. I would give credence of perhaps 15% that something specifically to do with consciousness causes deviations from quantum theory, with perhaps 3% credence that this will be experimentally detectable within the next 50 years, he says. If that happens, it would transform our ideas about both physics and the mind. There seems a chance worth exploring. So there you have it. In my opinion, in my mind, yes, there is a connection. This paper has put forth a very good overview of the hurdles that are involved in trying to understand this. But again, when I consider the miracles that Jesus did, and that he himself was in some way limited by people's belief, by what they thought was possible, and that he was therefore not able to do things. Remember Peter coming and walking on the water. Peter was going good until he looked around, and what did Jesus say? Why did you doubt? In other words, what Peter perceived to be real in some way changed what was actually happening. I mean, we all know you can't walk on water, right? And yet Peter was doing it. Peter was doing it. It wasn't by his own power that he was doing it. It was clearly by God's power, but there was a relationship between his belief in that power and the ability to actually do it. And the moment that he stopped believing it, when he started to doubt it, he lost the ability. Even though it was by God's power that he could walk on water, yet by the very fact that he began to doubt, he could no longer do it. And Jesus even said that all things are possible if you believe and you do not doubt. You'll be able to move mountains, etc. Things that seem absolutely beyond our comprehension, and yet Jesus said those very things. Well, keep thinking about this. We'll keep speculating, and hopefully we'll get to the answer. Until next time, God bless.